Good evening, everyone. Today we will start with spectrofluorimeter and phosphorescence spectrometer. Okay. So the word spectro, it comes from the word spectrum. This fluori, it comes from the word fluorescence, and meter is the device which is used for the measurement purposes, right? So combining this, we can say that spectrofluorimeter is a device which helps in the measurement of the fluorescence spectra. Okay, so we will be studying what is fluorescence in today's lecture. Then another thing, another important or the related emission spectra is phosphorescence, which is related to fluorescence, but it is not exactly fluorescence. We will see how fluorescence and phosphorescence they differ from each other, and uh, this phosphorescence it is also regarded as delayed fluorescence. Okay, and the spectrometer, which is used for the measurement of the phosphorescence, is regarded as phosphorescence spectrometer. Okay. Now, background, what is fluorescence? Fluorescence is nothing but the re-emission of the radiant energy that has been absorbed by the molecules in the form of visible light. Okay, so the main thing is the re-emission. So re-emission of the radiant energy. Okay, so the radiant energy, suppose we are having a molecule and we radiate it with a radiant energy electromagnetic waves, then it absorbs some of the light, it may transmit some of the light, and depending upon the nature of this molecule, it may emit some radiations. Okay, it may emit some radiations. Okay, in the what you call, in the spectrum of the visible light. Okay, so that is called uh, fluorescence. Okay, so one of the major important thing of the fluorescence is that when we are having this radiating this electromagnetic radiation, it will have a certain lambda, say lambda 0, and the wavelength of the visible light is say lambda 1. Then the lambda 1, it will be greater than the lambda 0. That means the emitted light, it is having a higher wavelength as compared to the incident electromagnetic radiation. Okay, so where we will be having a higher energy? Can anyone tell me?
Radiant as a incident lambda naught.
Yeah, in the incident lambda naught, we will be having higher energy. Okay, because we have initially discussed, if there is an increase in the lambda, then that means there is a decrease in the energy and vice versa. Okay, so since the visible light is being emitted at higher wavelength, that means lambda 1 is greater than lambda 0. In other words, the E0, if I say the corresponding energy associated with the lambda 0 is E0, and for the lambda 1 is E1, then we can say E0 is greater than E1. Okay. The complete process of the absorption and the emission in the fluorescence, it takes place within the order of 10 to the power minus 12 to 10 to the power minus 9 seconds. That means nanoseconds to picosecond. So within a fraction of a second, this the process of the fluorescence, it is usually completed. Okay. Then in phosphorescence, what happens? There is a delay in the emission in the light. Okay. Here also there is an emission in the light. Here also you will be having that lambda 1 will be greater than lambda 0. Okay. So all the characteristics of the fluorescence and the phosphorescence, it will be same. The only difference will be this process. Okay, the process over here will be much larger than this 0.9 seconds. Okay, so usually anything, if you are having say if you are having this phosphorescence say greater than yeah, 10 to the power minus 4 seconds, then it is regarded as the phosphorescence. And the phosphorescence, if you see, it is also within a fraction of a second, but the phosphorescence may go on for a few days also. Okay, so if you're excited today, then you may see the process of phosphorescence even after few days. Okay, so if you see delay in period, which is basically within a fraction of a second to few days. Okay, to few days. So combining this fluorescence and phosphorescence, we called that we have luminescence. Okay, the complete process of the re-emission, that means combinedly both the fluorescence plus phosphorescence, it is regarded as luminescence. Okay, it is regarded as luminescence. Now,
Excuse me, sir.
yes.
Sir, I had a doubt, sir. Sir, if in phosphorescence there is a delay in emission, and then in fluorescence there like the emission is pretty immediate. So, how will it impact the like when we look at it into a molecular level? How will it impact the behavior of the substance or the analyte?
Behavior of the I couldn't get you.
So, if suppose there are two substances A and
Uh,
B, so
okay.
A shows fluorescence and B shows phosphorescence. So
Mhm.
there, is there any from a physical point of view, is there any way we can mark out that this is fluorescence and this is phosphorescence? Is there a difference in their behavior?
Yeah, the behavior will be this. You have to pick up this when your this emission re-emission is taking place. Is it very fast or is it delayed? Okay, so from the analysis of the spectrum on a time resolved scale, that will tell you whether the molecule A is giving you fluorescence or phosphorescence, or the molecule B is giving you the fluorescence or the phosphorescence. Okay, and
And sir, and
yeah,
like that, the properties will also differ. When both of them show, one shows phosphorescence, other shows fluorescence. So according to that, their properties will be different.
definitely. Uh,
Okay.
uh, in nature, there are no two items, okay, which will show similar spectrum or same spectrum altogether. Okay, except some yeah, enantiomers. Okay, where you are having a mirror image of the chemical structure is a mirror image of each other. Except those, you will not find that the spectrum, whatever spectrum you talk about, whether it is an UV visible spectrum, whether it is an IR spectrum, whether it is a this fluorescence or phosphorescence, no two molecule will have same spectrum. See, you have your own identity, right? Suppose it is you, right? And the person B is your classmate. Okay, both of you are having similar characteristics. Similar characteristics means you have done class 12, both of you, 10 plus 2. After that, both of you have given JE, right? After that, you have taken admission in BME or BT, BM or BT, right? in our department at IIT Rourkela. So see, you are having so many common things or common traits among yourself, but you are still different from the other guy. Okay, so in the molecule region also it is the same. So molecule A is different than molecule B. So either the absorption spectra, or if it is a fluorescent molecule, it will also have the fluorescent or the phosphorescence this thing, not fluorescent this thing. All of these they will be showing some absorption spectra. Okay, and in addition to that, A and B may be phosphorescence or luminescence. They show phosphorescence or fluorescence or phosphorescence property. Okay, so depending upon these the characteristics or the molecular architecture of A and B, the absorption profile will be different, and also the fluorescence or the phosphorus property will be different. Okay, now am I clear?
Yes, sir. Yes.
Okay, now uh, let's we go to the next topic, which is regarded in layman's term. It is regarded as energy diagram. Okay, this energy diagram, it is also regarded as Jablonski diagram or Perrin-Jablonski diagram. So there is one extra R, so please PRRIN. So you have to cut out one of the R. Okay. So now what happens over here? If you see, we have some lambdas over here. So as we go from left to right, there is an increase in the lambda. Okay, that means if we go from right to left, the energy will be increasing. Sorry, right? Now over here I have drawn certain lines. The first of the line I have drawn ground singlet state. Then the second one is second electronic singlet state. Then I have drawn another one, first electronic singlet state. Then inter-system crossing, and then excited triplet state. Okay. Now let us take up to this say lambda 3. Okay, the fluorescence. I have drawn the fluorescence over here. So what happens is that if all the molecules initially they are at ground singlet state. Okay, and we all know that the molecules they are constituted of electrons, and the electrons they appears in pair in an anti-direction manner. Okay, so if one is moving clockwise, the other will be moving in anti-clockwise, the other will be moving in the clockwise direction. Okay, so let us represent them in this fashion. Okay, so when they are moving in the same direction, in the opposite direction, that is called singlet state. That is called singlet state. Okay, if both due to some reason both the electrons they start rotating in the same direction, then it is called triplet state. Okay, am I clear? If the electrons are moving in the opposite direction, then it is in a singlet state. If it is moving in the same direction, whatever direction it may be, either the clockwise or the anti-clockwise, doesn't matter, so that is regarded as triplet state. Okay, now you have to understand whenever we radiate any molecule which is present at the ground level, when we radiate this molecule with some electromagnetic radiation, the electrons, they gain some energy and they get emitted from here. Okay, so if you see in the ground state, the electrons are always present in the singlet state. Okay, in the singlet state. Now, when we irradiate the molecules with a particular radiation, okay, then what happens? Say one electron, it stays, because if the electron pair, the electrons, they appear as pair, and if you are having anti-parallel spin, then the net charge or the net electricity, it will be zero. Net field. It will be zero. Okay. Now, when you are irradiating the molecule with the radiation, one of the electron, it may stay at the ground singlet state, and the other, it will move to the higher energy level. Okay, but if you see, it is an singlet state also. Here also it is in singlet state. That means the direction of the spin of these electrons will be anti-parallel. Okay. Similarly, at lambda 1 also, if you have an electron, the other electron will be going up, and over there also it will be in the anti-parallel direction with that of the electron which is in the ground singlet state. Now we have to understand, when we get excited, then we have to relax down. Say for example, due to some reason you have been excited, so you are a person, and due to some incident, it may be some family problem, it may be some cricket match, if you get excited, then what your surrounding family members, they tell you, see, you have to relax down. Okay, you have to cool down. So in case of electromagnetic energy also, we have given the person or the molecules, in this case the person is the molecule basically. So we have excited the molecule with certain external stimulus. Now due to that, the electrons, they have gone to the excited state. Now they have to relax back. Now the process of relaxation, it is divided into two parts, radiative and non-radiative. Okay, if it is radiative, then visible light is being emitted during the process. If it is a non-radiative, that means it is losing some energy, but it is not in the visible spectrum. Okay, so suppose if you see, S1 and S2 both are in the excited state. Okay, but even though they are in, both of them, they are in the excited state, there is an energy difference. There is an energy difference. Okay, so if you see, the fluorescence can occur only from the S1, which is the first electronic signal state. So what should happen? The electron which has gone to the second electronic singlet state, it has somehow come to this first electronic singlet state. So it will lose some energy and it will come over here. And this process of losing energy and coming to the another excited state, the lowest energy of the excited state, it is a non-radiative process and the process is called internal crossing. Okay, in the excited state itself, it is trying to go for the internal crossing. Okay, so it is losing some energy while coming from S2 to S1. Okay, and this process, it is called internal crossing, and this process is a non-radiative process and there will be no emission of the visible light spectrum. Okay, now before I go forward to this S1 state, we can have another set of molecules which may go to this state directly from the ground singlet state, and in that case it will absorb lesser amount of energy. As I told you, as we are going from left to right, our lambda is increasing. So when we are coming to the lambda 1, so that means lambda 1 is greater than lambda 2. In other words, E2 is higher than E1. Okay, so if a molecule, it has the capacity to absorb Em having lambda 1, then the electrons, they will go from here to here. Another important thing here in the intercrossing, internal crossing, what is happening? You see that this what you call the rotation of the electrons, it has not changed. Okay, the rotation of electrons, it has not changed. Okay, that's why it is called internal crossing. It is crossing the energy levels, but it is not changing the rotation pattern. Okay, so internally it is adjusting, the energy is being adjusted. So from lambda 1 also, as you again give another electromagnetic radiation, lambda 1, then you can go to the S1 state. So to the S1 state, for coming to the S1 state, which is the first electronic singlet state, for coming to this state, we can see we can have two processes. First one, we make the system incident with an electromagnetic radiation of higher energy. It will initially go to a higher electronic singlet state, and then through the internal crossing it will come to the lowest electronic singlet state, and from there it may show the relaxation process, or directly it may absorb a lower amount of higher wavelength electromagnetic radiation, and it will directly go to the first electronic singlet state. Now what electromagnetic radiation, what means, what would be the wavelength of the electromagnetic radiation, what the molecule will be absorbing? It is the characteristics of that molecule, you cannot fix it. Okay, so a molecule A, it may absorb lambda 2. Okay, it may absorb lambda 2 to its maximum, and molecule B, it may absorb lambda 1. It will absorb the mostly the lambda 1. Okay, so our idea is to get to the first electronic singlet state. Okay, now once we have here the electrons, it loses energy and come back to here to the ground singlet state. Okay, and during this process it emits some visible spectrum. Okay, visible light photons it emits. Okay, now if you see, now here also the rotation of the electrons, it is anti-parallel, so it is coming to the singlet state. Okay. Now, while it is radiating some energy, see, from lambda 1 to S1, it has absorbed say 100 photons, say for example. Okay. And out of that, it has released say 20 photons in terms of the visible light. Okay. So how much energy is left? 80 energy or 80 photon, the energy of the 80 photons, this electromagnetic radiation, this energy is left, right? So what has happened? The electron which is coming back, it is having lower energy. Okay. So lower energy means higher wavelength. Okay. So lambda 3 is greater than lambda 1. Are you getting my point? Lambda 3 is greater than lambda 1. In other words, energy 1 is greater than lambda 3. So how this energy is lost? This energy is lost because it is emitting radiation. Okay, visible radiations. Okay, so the fluorescence, it is an radiative relaxation process. Okay, radiative relaxation process. Okay. Then in some systems, it might so happen that this fluorescence does not occur. So how will it come down to the ground state? So in those cases, what happens is that it crosses from S1 to T1. What is T1? T1 is the excited triplet state. T1 is the excited triplet state. And what we have told, in the triplet state, you will be having the spin which is parallel to the electron which is already present in the ground singlet state. So you will be having the electrons which are having parallel or the same directional motion. Okay. And then when it comes down, while it is coming down, it comes down to the ground singlet state as the anti-parallel moving this electron. Okay. And in the process again, suppose here I said 100 was there, here this inter-system crossing, over here you lost say 20. For the phosphorescence, you again lost the 20 packets of energy, and in the lambda 4, you will be having to the ground state, the transition it will take at 60 packets of, it will having 60 packets of energy. Okay. So lambda 4 will be much greater than lambda 1 or lambda 2. Are you getting my point? Lambda 1 and 8.
Yes, sir.
So this is the difference between this thing, this fluorescence and the phosphorescence. And if you see the why I call it inter-system crossing, because initially we were having this singlet state configuration, and while coming to the T1, the movement has changed. The electronic rotational movement, it has changed. And over here in the intercrossing, there was no change in the rotation of the direction of the electrons. Okay. Whether it was moving in the clockwise direction or anti-clockwise direction, it was maintaining that rotational movement direction of it was maintaining the direction of the rotational movement. Okay. But when it is coming from S1 to T1, that rotational this thing, it changes. Okay. So both the, again in the inter-system crossing, it is a non-radiating because it is losing energy just to get from singlet state to the triplet state. So that means in this energy diagram, we have two non-radiative processes. The first one is the internal crossing. Second one is the inter-system crossing. Okay. Then the radiative relaxation, it can either be the fluorescence or it can be the phosphorescence. Are you getting my point? So radiative, it may happen in two ways. Non-radiative, it can also happen in two ways. Okay.
Sir, during the internal crossing, like how energy is getting lowered because it is not radiating any energy, just is changing the state. So how that energy is used in changing the state?
How the energy is okay. Say you are in a class. Okay. You are in a class. You are having 30 students. Somehow, due to some yen or say or you take an example. You are in a class. Every one of you are sitting in the class, right? So you have benches and you have occupied some of the classes. Suppose you are this is the front bench, upper side, the lower side is here. So suppose you are in the backbench system. Okay, you are a backbencher. Okay, so it does not mean that backbenchers are always weak in studies. You will find many of the backbenchers, they are now the CEOs of big companies and all these things. So in fact, what I believe, the backbenchers are much more dynamic. Okay, so don't take it in a negative way. Okay, so suppose you have a backbencher. Now, if you want to move to the first bench, then you have to put in some energy to move to the first one, first row. Okay, but will that energy be sufficient to move out from your class to another class which you may have wanted to study in? Okay, say for example, you may have wanted to study MBBS. Okay, so whatever the effort you will be putting in within the class, it will be lost over here only. But even though you have done some work, you will remain within this class. You will not be able to migrate to another class. Okay, if you have to migrate to another class, you have to give another test so that you can be moved to the MBBS course. Okay, so that is the NEET course. Okay, so the energy required over here while you are putting your best efforts to come to the first row, you are while doing the work you are losing some energy. Okay, so that means when you come from a one state to the another state, you have to do some work. Otherwise, how will you come to this state? Say for example, over here you have an energy of 100, but at S2 you have an energy of 120. So when you want to come from 120 to 100, so you have to lose this 20. So how will you lose? Okay, so you have to lose that 20 packets of energy so that you can come over here. But it is happening within this system. It is happening within this system. Okay, it may also this transition may also happen while it is losing the energy. That means its wavelength is going up. If you see, when I was talking about lambda 2 and lambda 1, there is a change in the wavelength. Okay, there is a change in the wavelength, so it is losing the energy, and while losing the energy, the wavelength is changing. Am I clear now?
Yes, sir.
Have I been able to clear your doubt?
Sir, actually, that energy is decreasing from 120 to 110, like for example. So the energy is decreasing. So I was asking if that energy is being radiated, but since it is not
No,
being
it is not
radiated,
radiated.
so
That's what I
how
told.
that
There
energy?
are two
Uh,
relaxation
mm-hmm.
processes. One is radiative and one is non-radiative. So this process, internal crossing, it is a non-radiative process. It is losing energy, unlike over here. See, it is losing energy, and while it is losing energy, it is releasing some energy also. But in this case, it is not the case. It is a non-radiative this thing, and when it is coming from a higher level to a lower level, it is losing some energy, and correspondingly the wavelength is increasing.
Yes,
Okay.
sir.
Anything else?
No, sir.
Am I clear to you, or still you have some doubts?
Yes, sir. I have one more doubt, sir.
Yeah.
Sir, why there is delay in case of the phosphorescence as compared to the fluorescence? Like there is some intersystem
See,
crossing, but the delay is for like for.
if I slap you, you may react in a delayed fashion. If I slap your partner in the class, he may react very quickly. So it's the internal property of the molecules, how they will be reacting. And there might be some reaction, chemical reactions which may be going on within that, which may take some time. And as I said, this transition is, it happens very quickly. If you see, nanoseconds to picoseconds, it is a very small period of time. Okay, whereas over here we are talking about say milliseconds. Okay, say this is in millisecond and this is in nanosecond or picosecond. Right. So see, this is very fast. So the reaction what the fluorophores they are giving, it is very fast. It is simultaneously absorbing and almost simultaneously it is releasing the energy. It is immediately going to the first state, higher state, and then immediately it is coming down. And over here also, when there is a movement, it is also happening very fast. Okay. However, in the this phosphorescence, it is absorbing, then after some time it is releasing. So it is taking some time. This intersystem crossing, first of all, it would take some time, and then once it is ready and once it has achieved the T1 phase, then it will happen. So basically, this intersystem crossing, it may be one of the criteria. So in it, and it will depend on the molecular architecture of the molecules. Okay.
Yes.
Yeah. Spectrofluorimeter. So what happens? You have a radiation source, you have a monochromator, a specific wavelength, or you can also use a filter. It will be made incident onto the sample. It would have been this thing, your absorption spectrophotometer. You would have detector over here. Okay, but you do not want that. Okay, so what you do? You take the reading at 90°. So you have an entrance slit over here, then you have a monochromator, which will break down the radiation which is coming from here. Okay, And there, yeah, there will be an exit slit over here, and there is an entry slit over here. So lambda 1, lambda 2, all these things will be there. So it will be breaking down, then you will be having the detector, and then it is going over there. So in the fluorescence, if you see, there is a 90-degree arrangement. This is important. Okay, otherwise what happens? The the fluorescence signals, they are very small. Okay, they are very small. Okay, you get a very weak signal from here. The fluorescence process is very weak. Okay, the energy what you will be having, it will be very weak. Okay, so if you put it in the same direction, then the radiation, then you would have to put some filters over here, strong filter, to stop the incident light from here also. Okay. So what it will do, in comparison to this, the fluorescence signal would be very slow, and you will not be able to record the any of the stuff. Okay. So the arrangement, it is made at 90-degree so that the incident radiation, it does not reaches the detector directly, and you are able to manipulate the only the fluorescence stuff, and you can get the reading. Okay. Then light sources, in this case low pressure mercury lamp or xenon arc lamp, which is a continuous source of radiation, it is used. Okay, both of these sources provide a suitable spectrum of ultraviolet light that includes chemiluminescence. Okay, so in chemiluminescence, you excite the excite the sample in the UV range. Okay, cuvette material, if you are just working in the fluorescence and if you are not interested in the chemiluminescence property, then you can use glass. Otherwise you can use the silica. Okay, in modern spectrofluorimeter, you have this scene again, the same 90-degree arrangement. Apart from that, you take the radiation source, you attenuate the source using a beam attenuator, and it is used as a reference photomultiplier. It is taken as the input to the reference photomultiplier, and the difference between the sample and the reference, it is being amplified, and it is being shown as the spectrum. So molecular structure and the fluorescence, all substances do not show fluorescence. This is an important thing. Some exhibit under suitable conditions, and some may be converted to fluorogenic moiety. Okay, and so some exhibit under suitable condition. If you give them suitable conditions, say for example some pH, some molecules, it may so happen at a low pH it is fluorescent, at a high pH it is not a fluorescent molecule anyway. Okay, or some may be converted to the fluorogenic moiety. That means you have a molecule, to that you attach some another group which will make the system fluorogenic, and that is called that's why it is called converted to fluorogenic moiety. Usually it has been seen the molecules which have high absorbency, they show fluorescence. Okay, molecules or compounds with multiple double bonds and conjugated bonds, they may show this fluorescence. Okay, now presence of various substituted groups in aromatic or heterocyclic compounds, okay, especially the one or more electron donating groups like NH2OH, OCH3 on the resonating nucleus, it will promote fluorescence. Okay, so you have to have an excess of electrons into the molecular structure or the chemical structure, so that it shows fluorescence. Okay, if you have certain groups which are withdrawing the electrons from the main structure like COH, NO2, N double bond N, Cl, Br, I, I. So you know all the halides, they are very highly electronegative and they can withdraw the electrons from the main structure. Then such groups, they destroy fluorescence. Okay. Ring closure in aromatic compounds. If you add up various rings and make it aromatic in nature, then um, the molecule will show the fluorescence. Then there are various polycyclic compounds like vitamin K, nucleoside, purine, vitamin A. They show uh, fluorescence. Okay. Formation of metal chelates. They can show the fluorescence. Okay. Okay. They promote the fluorescence. In fact, metal chelates and position of chromophore, change in pH and solvent. They may alter the fluorescent properties. Okay. Then factors which can affect the fluorescence. The first one is concentration of the substance. You have to remember that while you are measuring the fluorescence, the solution has to be dilute. Okay. Otherwise, you will be having concentration quenching. Okay. So if why dilute? Suppose you are having one molecule which is giving some radiation. Now, if it is concentrated one, this emitted radiation, it may be absorbed by the another molecule. Okay. So over there will be vibrational loss due to the intermolecular collision and reabsorption of the emitted fluorescence. Okay. The presence of oxygen, it reduces the fluorescence because it has the capability to oxidize the fluorogenic materials. Okay, and this process is called reduction of the fluorescence. Due to the presence of oxygen, it is called quenching of fluorescence. Okay, and if it is high this thing, it is called concentration quenching. Then photodecomposition, there are various chemicals which may decompose in the presence of the photons. Okay, they will absorb photon and that energy is sufficient to decompose the molecule, and in that case there will be a reduction in the fluorescence. Okay, pH. In neutral and alkaline pHs, phenol is ionized and provides weak fluorescence. However, in strong acids, strong acidic pHs, phenol shows strong fluorescence. Okay. Then temperature and viscosity. Increase in temperature and decrease in viscosity results reduces the fluorescence. Okay. When there is an increase in the temperature or you are having the viscosity, you are reducing the viscosity, then the fluorescence will decrease. Then if you have some impurities like fluorescein or eosine within the sample, they will absorb the radiations, or sorry, these impurities, they are fluorescent and they will show you the fluorescence, so which you do not want. Then we have chemical quenching. In the chemical quenching, what happens is that collision of the excited molecules with other molecules or ions, it happens. Okay, so it is somewhat related to the concentration of the substance, but over here we were talking about that the same amount of molecules, they are uh, capturing the emitted light, whereas in the chemical quenching there can be another compound. Say for example, you are having a compound or a molecule A which is being solubilized in a solvent, say solvent C, then this solvent, it can absorb the visible light, then it will show the quenching effect. Okay, so that is there. And lastly, the interfilter effect. There might be some non-fluorogenic material within the sample which can absorb light. Here we are talking about the solvents. Here we are talking about another chemical which is present. Okay, so it will absorb this light which are being emitted, and it will reduce the fluorescence activity. Okay. Then the relationship between the fluorescence and concentration. in fluorescence there is an important parameter which is called fluorescence quantum yield, which is given by psi, and it varies from 0.10 to 1. Okay, what is this psi? Fluorescence quantum yield. It is nothing but number of emitted photons divided by number of absorbed photons. That means how many photons have been absorbed by the solution versus and how many, and the ratio of basically how many fluorescent photons have been emitted divided by how many number of photons which have been absorbed by the solution. Okay, so if you calculate this IT from here, we have seen that we can calculate what is the absorbance, and from there we can find out, and from the fluorescence we can find out the other thing. So the intensity of the fluorescence, it is given by this equation, IF equals to K I naught is the incident radiation, then 1 minus 10 to the power minus epsilon BC. Okay. Now you have to remember that um, if dilute solutions are used, then what happens? Then less than 2% of the excitation energy is absorbed, and usually under this condition, when there is less than 2% of excitation energy which is being absorbed, under this condition the fluorescence intensity, it becomes proportional to the concentration to this thing. This one is for when there is an high absorption coefficient. Okay, so you have to see that the solutions are dilute enough so that only a fraction of the fraction means only less than 2% of the incident radiation, they are being absorbed. Then phosphorescence spectrophotometer. So how to detect that? If you see there are two what do you call, blockers or choppers. Okay, now these choppers are 50% open and 50% blocked. So while you are um, exciting the sample, this chopper 1, it is open and the radiation source, it is going over here to the sample, it is exciting the sample, and at that time this second chopper, it is blocking the input to the detector. Okay, so there is no recording. So only after the excitation is finished, this first chopper, it is blocked, and the second chopper, it allows the radiations to come into the detector. Okay, there are other these monochromators and all these things, other things are also there, just to make you understand what is happening over here. I have just shown this thing. Apart from this, the monochromators and entry slit, exit slit, everything is there. Okay, so it is the basic way to basic what you call architecture for the measurement of the phosphorescence, and this device is regarded as um, phosphorescence spectrometer. Okay. So with this, I complete your this chapter, fluorescence spectrofluorimeter and phosphorescence spectrometer. If you have any questions, we can discuss.
So can we use this fluorescence technique for the DNA sequencing? Because as you have mentioned that the purine and other bases can show fluorescence.
Mm-hmm.
So can we use this technique for DNA sequencing, like studying the spectrum of the different bases like purine and then doing the DNA sequencing?
The thing is that, as I told you, because I am mostly from this instrumentation background, I'm teaching it for a longer time. I do not have much knowledge at this moment. I have to go through the literature again for the DNA sequencing. So, if uh, if there is a what you call if upon the excitation of the molecules, the amino acids or proteins, whatever you are telling, okay, if they are showing the fluorescence activity, definitely you can analyze it using the spectrophotometer. And from the lab perspectives, from my previous knowledge, I have seen that many people they do the gel documentation. Okay, so in the gel illuminator, what do you do? In the gel illuminator, after you have run the DNA samples and all these things, you put it in a UV illuminator, right? And then there is a window. From that window, you take the image. So what the UV illuminator is doing? It is falling onto the DNA samples or the base pairs, and it is giving some fluorescence over there, and you are measuring that fluorescence. Okay, so it is possible if you can isolate those, and then you can calculate or you can find out the concentration of those things in a particular volume. So how much is that base pair and all these things?
Okay, okay, sir.
It is possible. And talking about this UV illuminator, again I would say in the previous class I have shown you how you can do the um, analysis, image-based analysis for the UV visible spectrophotometer. So over here
Hmm.
also, if you can make a similar arrangement where your UV will be from the top, and if you have a small section of the gel which you put over there, and then at the 90-degree you make your arrangement in such a way that the fluorescence spectra it comes to the imaging system, then you will be able to measure the fluorescence using your homemade device also. Have I been able to make you understand?
Okay. Yes, sir.
Suppose this is your
Yes,
gel.
sir. Yes.
Okay, this is your gel. So you are having these patterns, right? Suppose you cut this gel part. You take this out. Okay. You fix an guided LED over here. It will be incident over here, and you'll be getting some transmission. But at 90-degree, you place an arrangement for recording the spectrum. Okay. Suppose like this, you make a slit. So UV is getting illuminating over here, and through the slit only a small amount of light it is going. Then you put a monochromator over here, and then it is breaking the spectrum, and then you have the camera. Say this is the camera. Okay, so it can record this spectrum. Now am I clear?
Yes, sir. Yes, sir.
Okay, so you can make your own stuff. See, my idea is to make you understand the things such that you can come up with your own creative ideas. Being in a technological institute, it does not mean that suppose if you try to go to say you are posted in Africa in the ground field and you do not have the spectrophotometer, but you may need the access to the spectrophotometer. Then what you will do? You will leave your job. You will not leave your job, na? Then you have to
Hmm.
think of the instrumental thing so that you can initiate your research and you can do the analysis in a better manner. Okay, so it's all about how you can apply your knowledge to a particular field. So you can take out the different bands over here, you cut this, you put it over here, and you find out how is the spectrum. So you can make this. So believe me, these are very easy to develop. It's just the human it's just your blockade, mental blockade basically, that we are not doing. And many people will tell you that even if you make that your spectrophotometer is not having resolution, what does that matter? How does that matter? If you want to go and buy a spectrophotometer, it would cost you minimum of 8 to 10 lakhs. However, if you want to make your own system, I guarantee you can make it within 5,000. Okay.
Yes, sir.
At least it will solve your own purpose.
Mm,
Yeah. Anything else?
no, sir.
Anyone else? No? Okay, then all of you have a Merry Christmas and enjoy your long weekend. We'll meet
Thank you, sir.
again on 28th